All right, in this much delayed but very anticipated video on solving quadratics, we're going to learn another technique for solving quadratic equations. So the first method we learned was solving by square roots, and we also learned to solve by graphing. Graphing is a pretty reliable method, and if you know how to use graphing well, you can always at least get to an approximate answer. But there can be times when it's useful to solve algebraically, because it gets you a more precise answer, and it also lets you kind of massage the equation in other ways. So we're going to learn another algebraic technique today. Now I want to quickly review what we know about solving by square roots and solving algebraically. So I start off with this problem, and when you see a problem with this structure where you can see an easy path to get to a square root, solving by square roots is the most straightforward method to solve. So in the case of this problem, we can see that we just kind of undo the order of operations, right? And first we'll add 20 to both sides, and we'll add 20 over here. And then the next line down, that leaves us with 3 times the quantity x plus 1 squared. And sorry, I'm trying to find my way around the keyboard here, equals 75. So then, of course, we would divide by 3. It's the next step we would undo. And that would give us x, in parentheses, x plus 1, end parentheses, squared, equals 75 divided by 3 is 25. So the next operation we do is the square root, because the squared operation is outside of the parentheses. So we'll square root both sides. But when we do that, that's when the equation splits into two parts. Because x plus 1 could equal 5, that's a square root of 25. But x plus 1 could also equal 25, or sorry, negative 5. That's the negative square root of 25. 5 times 5 gets you 25, and also negative 5 times negative 5 gets you 25. So x could therefore be 4, or x could be negative 6. Okay, so two solutions to that equation. Now there's this equation down here that just doesn't have a structure that's going to work for solving by square roots. We could move the 2 to the other side, sure, but then we'd be left with a 2x squared and an 8x on this side. And if you take the square root, you have to do the square root of the whole side of the equation. So although the x squared square roots nicely, this part does not. And the square root of 2x squared minus 8x is not as simple as just square rooting both of those terms. So you kind of end up in a situation where you're going to make the problem worse if you try to solve by square roots. So that wouldn't work for this problem. You need other tools, but we can use what we know about the properties of quadratic functions to help us. So we know you can sometimes factor a trinomial, and this can be helpful. So to understand why, it helps by starting off with just this little simple thought experiment. If a times b equals 0, this tells us something about the variables a and b. The only way you can multiply and get 0 is if one of those terms is 0. You can do 5 times 0, 25 times 0, 100 times 0, negative a million times 0, but something's got to be 0 in order to get 0 from multiplication. So in this situation, it tells us that either a or b must be 0. And knowing that can help us to solve some quadratic equations. So let's look at this example here. This is the factored form of the equation x squared. Sorry, I'm writing out in the wrong line. X squared plus 9x equals 0. So you could expand it to that. But if I leave it in factored form and I get rid of that, I can see something interesting about its structure. X times x plus 9 is equal to 0. Therefore, I know that either x is 0 or x plus 9 is 0. If one of those terms is 0, then when I multiply them, I get 0. So there's sort of the tip for how we're going to get our two solutions for that quadratic equation. We're not going to expand it, we'll leave it factored, and we'll solve it such that either x equals 0 or x plus 9 equals 0. And so this equation's trivial, that's already solved. For x plus 9 equals 0, we'll just subtract 9 from both sides, and then x must be negative 9. So there's two solutions to that quadratic equation. X is 0, and x is negative 9. You can write those solutions in set notation if you'd like. or I also accept it if you just write x equals 0 or x equals -9. So here's another one written in factored form. Again, we could expand it, but expanding it is actually not helpful. It's more helpful if we leave it in factored form. As long as this side is equal to 0, we know that either this term or this term must be equal to 0. So once it's already factored, the way that you solve it is you just set each of those terms up as its own separate equation. X minus 3 equals 0, or x plus 4 equals 0. And in the case of this equation, x must equal 3. And in the case of this equation, x must equal -4. So two solutions. If you can factor an equation and it equals 0 on the other side, then it's super easy to get to the two solutions. So here's one. It meets one of those criteria. It's set to 0 on this side, but this side is written in expanded form. And so I wonder if we can write it in factored form, can we solve it by factoring? So I need to think of two numbers that when I multiply them, I get -5, and when I add them, I get -4. 5 is prime, so that's helpful. It doesn't have too many whole number factors. And I think I can get there by doing -5 and +1. -5 times +1 is -5, and -5 plus +1 is -4. So there's my factoring. X minus 5 times x plus 1 equals 0. Now I've got two terms. When I multiply them, I get 0. So one of them has to be 0. X minus 5 could be 0, or x plus 1 equals 0. And so in this case, x must be 5. And in this case, x must be -1. Okay, so here's some practice problems to try, and we'll just work through these kind of quickly here. Again, I'll check and make sure this is equal to 0. Yes. So then we'll see if this expression is factorable. It's factorable if I can think of two numbers that when I multiply them, I get -24, and when I add them, I get +5. So I think +8 and -3 meet those criteria. If I do x plus 8 times x minus 3, so 8 times -3 is -24, and then 8x plus -3x would be +5x. That equals 0. Therefore, we've got two equations to solve. X plus 8 equals 0, or x minus 3 equals 0. And then the solution to this first equation is x equals -8. And the solution to the second one is x must equal 3. Okay, next one down. This is set to 0, that's good. And if I can factor this, then we can solve by factoring. If I can think of two numbers such that I multiply them to get 120 and I add them to get 22, then I can factor it. And I think there are two. What about 10 and 12? 10 times 12 is 120. 10 plus 12 is 22. So x plus 10 times x plus 12 is equal to 0. We've got two equations to solve now. X plus 10 could equal 0, or x plus 12 could equal 0. And in the first equation, x must be -10. And in the second equation, x must be -12. Okay, now this one's got an interesting structure because there is no middle term with x in it. It's just x squared minus 1/4 equals 0. But this one is a difference of squares situation. It's a difference of squares because x squared is a perfect square, and 1/4 is actually a perfect square. If you do 1/2 times 1/2, you get 1/4. So for the factoring of a difference of squares, it would be x minus 1/2 times x plus 1/2 equals 0. And then I treat each of those as an equation to solve. X minus 1/2 could equal 0, or x plus 1/2 could equal 0, and therefore x must be +1/2, or x is equal to -1/2. I want to point out with this problem that it's also possible to solve something like this, a difference of squares, by doing the square root method. All we would do is move the 1/4 to the other side of the equation, and we can say x squared equals 1/4. You square root both sides, and you get x equals -1/2 or x equals +1/2. So the square rooting method also works in a difference of squares factoring. And then there's this one. So right off the bat, this looks factorable. However, this is not set to 0. And I'm going to end up with a much tougher problem to solve if I factor this, and then I'm having to think of two numbers such that when I multiply them, I get -100. There could be an infinite number of possibilities, and having to sort through them would be painful. So I need to make that right-hand side be 0. So I'm just going to add 100 to both sides of the equation so it is equal to 0, and then see if I can still factor it. So this is x squared plus 60x plus 800 plus 100 is 900, and then -100 plus 100 is 0. So we add 100 to both sides. And now I need to try to factor this such that there are two numbers. When I multiply them, I get 900, and when I add them, I get 60. And I think those two numbers are 30 and 30 again. So this looks like a perfect square trinomial because this number is 30 squared, and this number is 30 doubled. So the factoring of this is x plus 30 times x plus 30 equals 0, or x plus 30 quantity squared equals 0. And so we can take the square root of both sides since this quantity is squared, but the square root of 0 is trivial, it's just 0. And so there's only one equation to solve in this case because there isn't a positive and negative answer, and both of our factors ended up being the same thing. So we only have one equation to solve. X plus 30 equals 0, therefore x must be equal to -30. Okay? So that is solving by factoring. It's easy to learn, difficult to master, but the two important things to remember are set the equation equal to 0, and then factor the original. And once you've done those, then you can solve each of the two factors as separate equations. There is some Khan Academy practice listed in the link for the video. There's also a Desmos activity for Angry Birds. If you're one of my students, you don't have to do this now. We'll do this in class when I see you next. But you're welcome to try it even if you're not one of my students. So I hope you enjoy that lesson. Have a good day. See you tomorrow.